choosing a convergence test. Now, this is actually from OpenStax Calculus Volume 2. This is actually from the tail end of Section 5.6. And it's a good idea to think about the process, the strategy behind choosing a convergence test. If you're looking at just a series that's not in a section, if it's in the root test section, there's a good chance the root test is going to apply. If it's in the section on the ratio test, there's a good chance the ratio test applies, integral test, etc. But if we just saw one in the wild per se, if I just threw a series at you, it's a good idea to think, how would I approach it? And this is actually just straight from the book. So I want to look at this. I don't always apply this in this order, but it is a good strategy to think of. It has all of our different tests in here. So if we have a series from n equals 1 to infinity of a sub n, our general strategy should start out, is it a familiar series? Is it a harmonic series? Is it an alternating harmonic series? Is it a p-series, a geometric series? And most of the time, you're not just going to have a p-series or an alternating harmonic series. You're not going to have something like that, but you very well may have a geometric series. So consider all of the ones that are familiar to us and start there. If it applies to one of those, then great. We know when the p-series and the geometric series, when they converge and diverge. Next thing you might check is the alternating series test. Is it an alternating series? Are we interested in absolute convergence or just convergence? And so we want to look there. So if this applies, then use the alternating series test. If we are only caring about absolute convergence, then we might move on to look at the series of absolute values. The next test would be the geometric comparison. We might often compare to a geometric or a p-series. So the comparison test or the limit comparison. Now, most often, the limit comparison test is the better of the two. That's just true. In general, the limit comparison test is the better of the two. If our series, the terms, contain a factorial or some sort of power, then it might be a good idea to try either the ratio or the root test. Now, if there are powers of something to the nth power, the root test is absolutely the best, hands down. Otherwise, we might try the ratio test. Okay, if there are factorials or exponents, that's usually a good idea. Last but not least is the divergence test. Okay, we can always look to see if something diverges. If the terms go to anything other than 0, then it diverges. But sometimes it doesn't give us a lot of information, so we might try the integral test. So generally we go in that order. Now, often I will say I check the divergence test first. Just real quick check in my head, is it going to infinity? Is it going to 7? Is it going to something other than 0? And that'll give us something to go with. So example 58. Determine which convergence test is the best to use and why. Then determine whether the series converges absolutely, or diverges. Well, just a quick glance tells me the terms here are going to 0. So the divergence test tells me nothing. All right, next, is it a p-series or a geometric? So that is our step 1. And this is definitely not a p-series. Okay, it's not alternating either. Okay, so of our steps, 1 does not work. Okay, so this is not a p-series, okay, or geometric. And I will write these out for this first one. Next, it is not alternating. Okay, so I do not need that second set. Is it similar to a p-series or a geometric? Yes, actually. We have an n squared over n cubed. All right, so this is approximately, this series here is similar, it appears, to 1 over n, the harmonic. Now that does not mean it diverges. That means we can, however, look at the limit comparison test. Okay, so that is really our third set. So let's go ahead and take the limit of n squared plus 2n over n cubed plus 3n squared plus 1 all over 1 over n. Now that limit is going to be, limit as n goes to infinity, all right, that will be an n cubed plus 2n squared over n cubed plus 3n squared plus 1. That limit is 1. All So by the limit comparison test, if the limit of the ratio of those two, okay, our b sub n, okay, that is our b sub n, it diverges. It diverges, so that tells us, therefore, sum from 1 to infinity of n squared plus 2n over n cubed plus 3n squared plus 1 diverges as well. And let's add this in here actually. This is by the limit comparison test. So go back and look at that if you need to. All right, number 59. And by the way, you can go to that URL there to check out this great textbook, OpenStax Calculus Volume 2. Determine which test to use and why. All right, well, to begin with, is this familiar? No, it is not familiar. All right, well, there's one down. Is it alternating? Well, yeah, actually, this is alternating. So we might look at our alternating series test. We might do that. Now, it does not look like, well, that factorial, that n factorial just kind of makes me think, maybe not. If we have factorials, we said in step 4 there, that we might try the ratio or the root test. So it is alternating, but I'm actually going to look at just this part right here. Okay, so my b sub n is the 3n plus 1 over n factorial. So I want to see what's happening with that, regardless of the alternating portion of that. All right, so if I take that, I'm going to do the ratio test. So n goes to infinity of 3n plus 1 over n plus 1 factorial over 3n plus 1 over n factorial. That is going to be 3n plus 4 over 3n plus 1. And then we've got our n factorial over n plus 1 factorial. Add my limit back in there. Okay, so that means this limit is the same as 3n plus 4 over 3n plus 1 times n plus 1. That limit is 0. Now, because this did not account for the alternating portion of this, that means that sum, okay, of -1 to the n plus 1 plus 1 over n factorial, this converges absolutely. Okay, because we took the absolute value of that, we are saying that this converges absolutely. Well, that means that the original series, n equals 1 to infinity, of -1 to the n plus 1 times 3n plus 1 over n factorial, that means this converges. That was, after all, an option. So we can certainly say that it converges. Right, number 60. A series from 1 to infinity of e to the n over n cubed. Okay, well, first, it is not familiar. It's also not alternating at all. It doesn't look similar to a p-series because we have the e to the n up there. But one thing we might check is the limit, since I'm not seeing powers or factorials. I don't think the ratio of the root test can be helpful. Let's just go ahead and explore a bit. And we'll take the limit of e to the n over n cubed. Okay, well, if I take the limit there, they're both going to infinity. Infinity over infinity, so I can apply L'Hopital's rule. This would be e to the n over 3n squared. And let's go ahead and apply that again. L'Hopital's rule would be e to the n over 6n. And I can still apply L'Hopital's. It's still infinity over infinity. E to the n over 6, which is infinity. So the terms are actually going to infinity. So therefore, our series from n equals 1 to infinity of e to the n over n cubed diverges by the divergence test. Okay. Number 61. Hopefully, let's go back to 61. All right. Hopefully, looking at this series right here, something just jumps out at you. Okay, we can start going down our list. Okay, it's not familiar. It's not alternating. It doesn't look like it's going to be similar to anything, a p-series or a geometric. But hopefully your brain is just screaming at you, root test. This looks like it's something from the root test because we have an nth power on both. All right, so the root test says we'll take rho equals the limit, as n goes to infinity, of the nth root of the absolute value of our an. So this will be 3 to the n for n plus 1 to the n. Every term in that is positive. So this is going to be the nth root. This will be limit as 3 over n plus 1. And that limit is 0. So based on the root test, if our rho is between 0, if rho is between 0 and 1, it converges absolutely. If rho is greater than 1, it diverges. And if our rho is, that's about all we need right there. We don't need anything else. It is between 0 and 1, including 0, so this converges absolutely. Sum, n equals 1 to infinity, n plus 1, 3n over n plus 1 to the n. Therefore, that converges absolutely. Which means the series converges. Last question we have here is a mixed bag to see what's going to happen with these. The sum from n equals 1 to infinity of 2 to the n over 3 to the n plus n. Okay, this is not familiar. This is not alternating. Might be similar to something, so let's see term by term. 2 to the n over 3 to the n plus n. If this is less than or equal to a geometric, which in this case it looks like it might be to 2/3 of the n, let me write that differently. The denominator on the left is bigger, always, for all n. Therefore, that is going to happen. Now, this converges. In fact, it converges to, let's see, our first term, that'd be 1 over 1 minus 2/3. So this actually converges to 3. We don't care what it converges to because it doesn't help. But because this is less, okay, and the sum of n equals 1 to infinity of 2/3 to the n converges, we can say, therefore, sum from n equals 1 to infinity of 2 to the n over 3 to the n plus n converges, okay, by the direct comparison test. And actually on the last one right there, it converges by the root test. Alright, so recognize when you need to use each of these tests, since we do have a whole bunch of them. Now, this next thing is a summary, and I'm just going to scroll over this pretty quietly. I'm going to scroll through this because this is useful to have. It's a table that's in the book. I would suggest you actually go to the book and look at it. Go to this URL. We have the divergence test. Geometric series, that is one of those are two familiar. Geometric and p-series. Next, we talked about the comparison and limit comparison test. With the divergence test, we discussed the integral test. And I again suggest you go back and read these and make sure you're comfortable with using whichever one. Integral test. Then we have our alternating series test, which only works for alternating series. Then we have the ratio and the root test, the last two that we discussed. All right, that is the end of this section. Hopefully, you can now feel a little bit more familiar with all of those different tests. That's it.